Hello everyone, my name is Li-Hsing Yen from National Yangming Jiaotong University. Today my topic is Incentive Stable Matching Protocol for Service Chain Placement in Multi-Operator Edge System. Here is the outline of my talk. First, introduction followed by system model and problem definition. Then I will show the proposed mechanism and the simulation result. Finally, a conclusion. Network function virtualization, NFV, is to consolidate network functions onto industrial standard servers, switches, and storage hardware. This has been done by utilizing virtualization technology such as virtual machine and virtual networks. And we call the software instance that realize network function as a virtualized network function. So NFV is to turn physical network devices into a virtualized network function. These virtualized network functions are to be placed in our infrastructure called NFV infrastructure or NFVI. Service function chaining, SFC, is to dynamically chain VNFs in some way to provide specific NFV-based network services to users. SFC is a promising use case of NFV. Okay, here we have an example of a service chain that comprises of 5 virtualized network functions. Service chain embedding or service chain placement consists of 3 tasks. The first one is VNF placement, that is to place VNFs into NFVI. Then the second task is to chain these VNFs together. We call it SF chaining. The third task is service function scheduling, which is not covered in this paper. Traditionally, service chain embedding is in the data center. That is, we use data center as NFVI. However, in this paper, we consider edge computing. Edge computing provides storage and computational resources close to end users. Edge system could be used as NFVI for service chain. Here we consider geo-distributed MEC servers owned by a service provider or SP. So the system model is we have multiple geo-distributed MEC systems owned by multiple operators. And we have multiple service chains to be deployed into this kind of NFVI. So related work, there have been some studies toward SFC in edge or cloud environment. But among them, only one consider multiple service providers. And this study is for cloud computing instead of edge computing. So here is our system model. We have multiple service chains, multiple service providers, and we have multiple areas. In each area, a service provider may have a MEC edge server for service chain placement. In the first step, service chains first send inquiry to each service provider. Okay. The inquiry message contains ID of the service chain, resource demand, bandwidth demand, and area demand of the service chain, and a latency constraint associated with the service chain. After getting an inquiry, the service provider finds out the minimum cost deployment for each service chain. Okay, considering his computing and communication resources in each area. For this problem, we should consider VNF placement and also SFC routing constraints. So basically, it's an integer programming problem. Then, after figuring out the minimal resource cost for each service train deployment request, the service provider responds with X price. That is the minimal deployment cost and the amount of allocated resources to each service train. Based on the information, service train can then propose the bid price to each service provider, starting from the most preferred one. Then the request could be accepted or rejected. If the request is rejected, the service train could turn into another service provider for possible deployment. The whole problem is to maximize the so-called social welfare. The social welfare is defined as the summation of this term. Here, the summation is for every service provider and for every service chain. We have an indicator variable zkn, which is 1 if service chain sk is deployed by service provider pn. If this is the case, then we may earn this component. That is the difference between the service train's budget, that is the maximum buying price, and the service provider's deployment cost. That is the service provider's ask price. Then we model this problem as a many-to-one matching with two-sided preferences between service chains and service providers. For each service chain, it has preference over service providers. For example, here, service chain S1 may prefer P2 to P1 to P3, for example. On the other side, each service provider also has a preference over service chains. In this example, service provider P1 may prefer S2, Sn, these two service chains to P1 alone. And he prefers P1 to another set of service chains. And the result is a matching. That is, in this case, service chain S1 is matched with service provider P2, for which the indicator variable z1 is 1. So in the matching, we say it is a two-sided preference. That means each party has his own preferences. For a service provider Pn, his preference is over a set of service chains, S prime. And the preference value could be expressed as this, the summation of the difference between service chain's budget and service provider's deployment cost. For each service chain, it also has a preference over each service provider. The preference value considers resource surplus, because when a service chain demands a certain amount of resource, the service provider may provide an amount of resource that exceeds the demand. Of course, the surplus is welcome, but the preference over the surplus should obey the law of diminishing return, like these two functions. I omit all the details here. Then with this model and assumption, we may use the many-to-one deferred acceptance or DA algorithm for this kind of matching. In DA, clients that is service chance proposed to service providers. Okay. And service providers may reject or accept the proposal. Okay. The result is incentive stable. That is, there is no blocking individual and blocking pair. Okay. That means no individual or pair of parties will be better off by deviating from the matching result. However, the result is the optimal stable matching result for service chance. Okay. And the result is also the worst stable matching for service providers. So the result favors service chance instead of service providers. And so for this reason, we want to make the matching egalitarian. Okay, so we apply T-argument to the result of DA. Okay. The best idea is we have many stable matchings. Okay. On the left-hand side, the result is optimal to service chance, but worst to service providers. Okay. And on the right-hand side, the result is optimal to service provider, but the worst to service chance. We have a lot of matchings that is between. Okay. And the result on the left-hand side is the result generated by DA. And we want to find out other results that is between these two extremes. And we perform the simulations to measure the performance of the proposed diagram. Here are the simulation settings. The first experiment is to study the effects of the length of service chance. Here we consider 20 service chance. And we change the number of V and Fs in the service chain from 1 to 10. Okay. That is, a service chain may contain 1 to 10 V and Fs. And we measure the social welfare and also the number of matched service chains. Okay. We can see that the social welfare drops as service chain becomes longer, okay, which is expected because when the service chain becomes longer, it demands more resources. We observe the same trend in terms of the number of matched service chains. The second experiment is to measure the effect of the number of service providers' coverage areas. Okay. Here, each service provider equally allocates all his computing resource to all areas. So when the service provider has more areas, the resource in each area becomes much smaller. Okay. And here we assume that each VNF is allowed to be deployed in one of 3 areas randomly selected from 5 areas. So we change the number of areas from 1 to 5. Okay. As can be seen, the social welfare increases as resources distributed to more areas, okay, from 1 area to 3 areas. Okay. But after that, social welfare actually decreases because at that point, okay, when we have more than 3 areas, the amount of resource per area actually decreases. Okay, so that's the reason why social welfare also drops. Okay. And we observe the same trend for the number of matched service chains for the same reason. And we also measure the effect of different quotas. Okay. Quotas here mean each service provider divide his resource into a number of quotas. Okay. Each quota has the same amount of computing resources. Okay. So we changed the number of quotas per service provider from 1 to 15. Okay. And we measured the social welfare and the number of matched service chains. On the right hand side, we can see that the number of matched service chains increases due to more quotas at the beginning, when we increased the number of quotas from 1 to 4. Okay. But after that, when we have more quotas, okay, the number of matched service chains actually decreased. The reason is that we may have lower resource quantities per quota if we increase the number of quotas. Okay. On the left hand side, we can see that the social welfare actually increases. Okay. When we increase the number of quotas from 4 to 6. Okay. Not the same as the number of matched service chains. Okay. The reason is when we increase the number of quotas from 4 to 6, we actually increased the social welfare because we have a lower resource surplus for each quota. We also compared the proposed diagram with other approach named BSAM, okay, in terms of social welfare and the number of matched service chains. Okay. When we increase the number of service chains from 5 to 20, we can observe the effectiveness of the T-diagram. Okay. When we have like 18 to 20 service chains. Okay. So the effectiveness of the T-diagrams can be seen in this range. Okay. Also, the BASM does not perform as well as the proposed approach when we have more service chains. Okay. Actually, the BSAM served more service chains than the proposed approach, but these service chains are with lower social welfare. So in terms of social welfare, BSAM has lower social welfare but more number of matched service chains. The conclusions. We have studied service chain placement in multi-service chain, multi-service provider edge system. And we have formulated the social welfare maximization problem. We have proposed a two-sided match mechanism based on DA and T-diagram. And the simulation results show that the social welfare may not be aligned with the number of matched service chains. Thank you for your listening.